Hi everybody.
Hello.
My name's Louise Gagnon. I'm a rising high school senior, and I've been working with the JJMO for the last 2 years. So welcome to Second Saturday Stars. Tonight I'm going to be talking about some of the current theories on the beginnings of the universe. So, in the beginning, there really wasn't much to look at. In fact, there was nothing. Time and space didn't exist, and there was no matter, no energy. And then, for some reason, the universe began with a bang. A pretty big bang, in fact. It was a universe-wide bang. We're not really sure how or why that happened, and that's one of the most pressing questions in theoretical physics today. Where the universe came from. But I'll come back to that. So, the very first moments of the universe's existence were not very pleasant. The universe was incredibly hot and dense. It was so dense that all matter and energy was condensed into one tiny point, and properties like mass and charge really just didn't have meaning. It was so hot. The first 10 to the negative 43 seconds, a short time, of the universe's existence is called the PLANCK epoch. This is an era that modern physics can't really describe. And I'll explain why. So, in our universe today, we're familiar with 4 forces that govern how things interact in our universe. I brought some visual aids. They're peppers. So, the 4 forces are, there's gravity, which we're all pretty familiar with. You know, it makes things fall and keeps things in orbit around stars and stuff. And then there are 3 forces that act on the subatomic level, which are electromagnetism, well named, has to do with electricity and magnetism. The strong force, which hold things together in the nucleus of an atom. So it holds together the protons and neutrons together into a nucleus, and it holds together the smaller particles that make those up. And then there's the weak force, which has to do with radioactivity. And so you can imagine the 3 quantum forces, electromagnetism, the strong and weak forces, as these 3 peppers. You know, they're all essentially the same thing. They all kind of... Oh, geez, okay. They all kind of taste the same. And, you know, they're different colors, but essentially they are the same pepper. You know, if we wanted to, we could describe... Oh yeah, I got a volunteer. If we wanted to, we could describe these 3 peppers with one mathematical equation. And modern physics has been able to do that. Gravity, if I can find it, is more like this jalapeno pepper, which, unlike these 3 forces which act on the subatomic level, this pepper, it tastes totally different. It fulfills a different role in cooking. You know, this is for spicing things up, and these are for sweetening. In the same way that gravity doesn't act on subatomic particles, gravity only acts on, you know, the big things, planets and stars and galaxies and people and stuff. And so modern physics right now doesn't have a way to describe all 4 peppers with one mathematical equation because gravity is so different. And that's why one of the reasons why we have trouble describing the first moments of the universe's existence. I think we can probably put the peppers down. I don't think they're going to balance. Fortunately, the Planck epoch didn't last very long, and after that came the Grand Unification epoch. That was also pretty short, lasted from 10 to the negative 43 to 10 to the negative 36 seconds after the Big Bang. And the reason it's called Grand Unification epoch is because gravity split off from the other 3 forces. It wasn't so hot that that all 4 forces were indistinguishable from each other. And so equations of theoretical physics can describe these 3 peppers. They can describe how electromagnetism, the strong force, and the weak force could unify into one force. And so that's why it's called the Grand Unification epoch, because we have a theory of unification that works during this period. But it was still really, really hot. So hot that, you know, properties like mass and charge still had no meaning. Then things got really big. this period's called inflation, and it is arguably, I've got a timeline down here, the most important period of time that I'm going to talk about today, in terms of the universe's evolution and getting the universe to the way it is today. So, inflation was very short, again, lasted from 10 to the negative 36 to 10 to the negative 32 seconds after the Big Bang. And it was a period of really intense expansion. Like, not the kind of expansion of the universe that's happening today, although that is, you know, legitimate. In inflation, areas of space the size of an atom were blown up to the size of our solar system in that incredibly short period of time. And this intense expansion was a really critical part of the universe's evolution. Although it does sound kind of crazy. Like, the other two, you know, the PLANCK epoch and the Grand Unification epoch, you know, those make sense. If the universe is tiny, it's going to be really hot and dense. But inflation sort of just seems to come out of left field, right? But it turns out that inflation, a period of really intense expansion, was actually necessary for our universe to look the way it does today. The inflation theory is relatively recent, so, you know, the people who came up with it are still alive, unlike with, you know, gravity. It was created to solve three main problems, one of which was the fact that our universe is very uniform. You know, if you look billions of light years away, actually, and we're doing that in this background image. This is from the Hubble Deep Field Telescope, which is where they point the Hubble telescope and look as far out as they can. And even, you know, billions and billions of light years away from Earth, the universe is pretty much the same. You know, the ambient temperature is pretty much the same. You know, it's made of stars and galaxies and stuff and planets. So the distribution of matter and energy across our whole universe is pretty much uniform. And that's pretty unlikely. It's pretty unlikely that, you know, areas of the universe, billions of light years apart from each other, so far apart that they couldn't have influenced each other, somehow evolved identically to have the same distribution of, you know, matter and energy. And so that's where inflation comes in, that it took place so early in the life of the universe that things didn't have time, variation didn't have time to occur. Inflation occurred quickly and early enough that, you know, there wasn't time for matter to clump up into more chunk here and, you know, empty space over here. And so inflation basically smoothed everything out, which is what allows us to have the universe we live in today, where, you know, we don't live inside some kind of massive black hole, and space isn't just empty either. So, inflation ended, and the universe kept expanding as usual, as it does today. Then came the ELECTROWEAK epoch. It lasted until 10 to the negative 12 seconds after the Big Bang. And so during this time, gravity had already left the Pepper family, and during this period, the strong force, things cooled off enough for the strong force to become distinguishable from the electromagnetic. We live in a universe without the strong force now. The strong force, it was cool enough that the strong force was distinguishable from the electromagnetic force and the weak force. But these two forces were still united. And we can describe that with modern physics. So modern physics still works, don't worry. And it was during this period that things cooled down enough for properties like mass and charge to appear. And actually, you know, individual particles were able to be differentiated from each other because there was enough, you know, space and low enough temperature. So the universe at this point was sort of a dense smoothie of two types of particles: gluons, which are what they sound like, they glue things together. They, you know, glue together the quarks, which make up a proton or a neutron, and they glue together those protons and neutrons into a nucleus. And quarks, which are really tiny fundamental particles, which means they don't have any smaller parts. Really tiny particles, which today make up bigger particles like protons and neutrons. So in our universe today, quarks don't exist on their own. Quarks only exist in pairs or triplets to make up bigger particles. But during this time, it was too hot for quarks to stick together. And it was so hot that just out in space, you were getting, you know, just crazy high energy quantum interactions to form exotic particles like the Higgs boson. If you've heard of the Higgs boson lately in news, it has to do with giving particles mass, so it's pretty important. It's good to have mass, although maybe not too much mass. And it's conditions like these, that we sometimes try to recreate in particle accelerators, because we want to try to get these crazy high energy quantum interactions so we can make all those fancy particles, because they don't really exist just out in the universe. We can't go looking for them. So, when it cooled down enough for the electromagnetic force and the weak force to split, to become distinguishable from each other, this was about 10 to the negative 12 seconds after the Big Bang, lasted until 10 to the negative 6 seconds after the Big Bang. This was called the QUARK epoch. And it was still too hot for particles to stick together to form bigger composite particles, but the universe did get, a new particle was added to the family. So we had quarks and gluons before, and now theories predict that we would have also had leptons. So these are all fundamental particles, which means they're not made up of smaller particles, as far as we know. Leptons are like the electron and its cousins. The electron is the one that orbits atoms. So the universe was still really hot, really dense, and made of 3 types of particles. Okay, so around 10 to the negative 6 seconds after the Big Bang, things cooled down enough for quarks to stick together. You can see, I can't do that, up there in the top, you can see the proton and a neutron, and those circles inside with the letters in them, those are quarks. So different arrangements of quarks give you different types of particles, and gluons hold them together. So during this period, the period of baryogenesis, baryons are particles and genesis is creation, so this is when particles are being created. Particles were being synthesized just out of empty space in matter-antimatter pairs. And antimatter does exist outside of science fiction. It's just we don't run into it very often in our universe today, because when an antimatter particle encounters the corresponding matter particle, they both annihilate into a blast of energy. But during this period, it was so hot that quarks were just sticking together into, say, like a proton and an antiproton. Those would, pop up out of a quantum field and annihilate each other, and only to be replaced by another pair. And so this was just happening continuously, because the universe is so hot. But for some reason that we still don't understand, another problem in theoretical physics, I guess, just has a lot of problems. For some reason, by the end of this period, there was somehow more matter than antimatter. When it cooled down enough that particles weren't being continuously created and all the antimatter was annihilated, we somehow had a little bit of matter left. And that's why this is a pretty important period, because it's the reason why our universe exists. If there hadn't been an imbalance in matter and antimatter, then they would have just all annihilated each other and we'd have an empty universe, which wouldn't be that great. And we're still trying to figure out how we ended up in a universe that's made of matter. But anyway, by about 1 to 10 seconds after the Big Bang, the universe was entirely made up of normal matter. And it's stayed that way, fortunately. Okay, so now we're going to jump from fractions of a second to the next 380,000 years. Don't worry, we're not going through the entire history of the universe in, 10 to the minus 6 second intervals. So, not much happened for the next 380,000 years. The universe, because all the matter and antimatter had basically been annihilated, the universe was mainly made of photons, which are particles of light, and it was opaque. I'll explain why that is in a second. It was cool enough that nuclei, atomic nuclei, could form, so you could have hydrogen nuclei, they just didn't have electrons orbiting them, because it was still too hot for electrons to fall into orbitals around atoms. But it was, and in fact it was hot enough that fusion was just taking place in open space. Fusion today only happens in the cores of stars and maybe in a laser lab somewhere in Europe. So fusion takes a lot of energy and a lot of pressure, but it was just happening in open space. And so some hydrogen was being fused to make helium, deuterium, which is a heavier version of hydrogen, and lithium. But it was still too hot for electrons to fall into orbitals around those. And I've got another visual aid. You remember, if anyone was here last month, you might have seen Bob use some light-up fidget spinners. And so, in terms of visual aids, the gauntlet has been dropped. So, really going all out tonight. So, in explaining why the universe is transparent today, I have this gunk from Instagram. So, if you think about a thing that's transparent, things are transparent because light can pass straight through them without interacting with that thing. And if something is opaque, it means light can't travel through it without hitting it. You know, light can't travel straight through my hand. It, you know, gets bounced around in the skin particles or whatever. And so, in the early universe, before, there were just electrons everywhere. Light couldn't just travel through space the way it does today because it would, you know, be bouncing off electrons, getting absorbed and re-emitted. But as the universe expanded and cooled, electrons fell into orbitals around atoms, leaving empty space between them. So if you imagine the, I don't know, how well can you see this?
Good.
Okay. Oh, okay, great. Thanks. So if you imagine the blue sticky stuff is electrons, and the white balls, white styrofoam balls are atomic nuclei. Right now this universe is pretty opaque. Light can't really travel through it because there's just electrons everywhere. But as this slime universe expands and cools, I guess, well, it has some problems because this universe doesn't have great tensile strength, and it's probably going to rip at some point, which isn't great for its inhabitants. But if you can see, as this universe expands, the blue slime junk becomes, it collects around the white styrofoam nuclei, leaving in between this transparent space. And so that's basically what happened with the universe. Electrons collected around nuclei so that there was a lot of empty space for light to travel through. This universe is also ripping in half, so yeah, that's the end of that. That one's not going to develop life, I guess. And so, at the end of the opaque universe, basically light particles they bounced off their last electron and then just traveled out into space. And we can actually observe this light today. And that's why, basically, when the universe becomes transparent, that's when astronomy starts to become the best tool for understanding the universe. Because we can actually look at things. And one of the great powers of astronomy is that we can actually use it to look back in time. So, we can observe this light from the beginning of the universe because light travels at a finite speed. So if we look at something that's 10 billion light years away, that means it's taken 10 billion years for that light to reach us. And so the image of that thing is 10 billion years old. You know, if it's a star, it might not even be there anymore. But it would take 10 billion years for us to find out that that star is gone, for that light to reach us. And so basically, the farther out into the universe we look, the farther back in time we're looking, because it's taken longer and longer for that light to reach us. And so basically, if we look far enough out into the universe, we can see the end of the opaque period. We can see the light that bounced off those last free electrons. Now, this doesn't mean that, you know, it's bright everywhere, even though there is light permeating the whole universe from the beginning of the universe. It's not, you know, bright out at night or anything. And that's because as light travels towards us, the universe is still expanding. And so as light travels through space, that light gets stretched out. And so that means that by the time that light reaches us, it has a much longer wavelength than it did when it left the source. So light that could have been in the visible spectrum has been stretched out so much that that our eyes can't detect it anymore. And the light from, I guess the farther away light is, or the longer light has to travel, the longer it gets stretched out. And so light from the beginning of the universe has been stretched out a lot, from, you know, visible range all the way to microwaves. And microwaves are pretty long. Not like the appliance, the wave of light. And so that's actually what this image is back here, this blue thing. This is an image of the microwave radiation that permeates the entire universe from that transparent period. This is like when you see static on a TV or a radio, I think about 1 to 2% of that is what's called the cosmic microwave background radiation. You know, it's just kind of everywhere. And we can take a picture of it, which is pretty cool. We can take a picture of the beginning of the universe, basically, with a telescope. Okay, so over the next 150 million years, not a lot happened. The universe just sort of chilled out. Because for more stuff to happen, the universe had to cool a bunch. The universe cooled from a rather toasty 4,000 Kelvin to the much more reasonable 60 Kelvin. Kelvin is a scientific unit of temperature measurement. It's the same like steps as Celsius, but it starts much lower. So 0 Kelvin is absolute zero. That's the coldest it can get anywhere in the universe. So 60 Kelvin is pretty cold, but not as cold as space is today. Space today is closer to 0 Kelvin. Just for reference, water freezes at 273 Kelvin. So 60 Kelvin is pretty cold. And 4,000 Kelvin is pretty hot. That could be, I'm not sure how hot that is in Fahrenheit, but it might be as hot as the surface of the sun. Pretty hot. So, after, 150 or so million years, structural formation began to take place. And, structures are important. We need them today. The reason we have structures in the universe today, like galaxies and stars and stuff, is because the early universe wasn't completely uniform. If you remember when we were talking about inflation, inflation was what allowed our universe to be pretty uniform, but it wasn't entirely uniform. I have the final visual aid. Can you turn the lights again? I think that helped. Okay, so if you imagine this balloon is the early universe, and as you can see, it's pretty even. Sharpie is pretty evenly distributed across this balloon universe. And so this is like the universe before inflation. Matter and energy are pretty much uniformly distributed, but when inflation happens, you can see that tiny, well, there's some matter escaping this universe, I think, but tiny fluctuations in the density of Sharpie distribution have led to pretty large-scale structures in this universe. And so these things, these bigger clumps of matter and energy are what will someday become galaxies. Okay, thank you. That's actually, that difference in distribution of matter and energy is actually what we're imaging when we take those images of the cosmic microwave background radiation. If you can see up in the corner over there, there are 3 different images spliced together. We've sent up 3 different satellites, at least, to take images of this radiation. And you can see there's sort of different colors. I guess the more warm-colored areas, like the reds and yellows, are places where there was a higher density of matter, and so more light was coming off that matter. And the blues are where there was less matter. This is still barely detectable variation. If you look at, we had to send up like 3 satellites to get a really good picture of it. But it's still very important variation, because that first satellite, Kobe, in 1992, on the left, it gives you a pretty blurry image, but that image was one of the ways we proved the Big Bang Theory. And that's kind of what astronomy does. Theoretical physics can make predictions, and that's great and all, but without astronomical, observational evidence, that's pretty much meaningless. And that's basically what these satellites have done. That's why we sent up 3 of them. Because the Big Bang Theory makes, the equations of that make predictions about how much variation we'll see in these images. And other theories about the beginning of the universe make different predictions. And so the fact that our observations match the predictions of the Big Bang Theory means that that's very strong evidence for it. And so, it's good astronomy. So, around 150 million years after the Big Bang, 150 million years after the Big Bang, normal matter was still too hot to condense into stars and galaxies. So gravity, likes to pull stuff inwards. So, if you have basically, the universe is basically a big cloud of hydrogen gas, and places where that's denser, gravity is trying to pull that gas inward to, make a star or something. But energy, if you put your hand on a cold thing, the heat from your hand will disperse into the colder area, because energy doesn't like to pull together. Energy likes to be spread out evenly over the universe. And so energy which was clumped together, was pushing outwards to try to achieve thermodynamic equilibrium, and gravity was pulling inwards to try to clump matter together. And so basically the two forces balanced each other, and not much was happening with normal matter. Dark matter, though, fortunately, doesn't play by those rules. You've heard of dark matter. That's another thing we discovered with astronomy, not theoretical physics, because when we looked at galaxies, physics predicted that they'd be spinning at a certain rate, but astronomy told us that those galaxies were actually moving a lot faster than they should be, given how much mass they have. And we realized that there's some substance that makes up about 95% of our universe, called dark matter. It doesn't interact with us in any way except through gravity. And we still don't know what it is. But we can observe it through its gravitational pull on other objects. And so when dark matter began to clump together into galactic-sized conglomerates, it sort of dragged normal matter along with it. And when things cooled down enough, the first galaxies formed inside masses of dark matter. And so galaxies today have massive halos of dark matter surrounding them. And the fact that dark matter clumped together earlier than normal matter meant that galactic formation could happen a lot earlier than it would have otherwise. Which is nice, I guess. You know, we got kind of a head start there. So, oh sorry, I was going to mention that the date down there, 500 million years. The oldest galaxy we've been able to observe with a telescope is from about 500 million years after the Big Bang, which is a long time ago, considering that the universe itself is 13.8 billion years old. So that's a pretty old galaxy, one of the first ones. Stars are important too. The first stars formed, we believe, from calculations, that the first stars formed around 560 million years after the Big Bang. And because there was a lot of gas just floating around in the universe, there was a lot of mass to be incorporated into those stars. And so the first stars were very massive and very short-lived, because generally, a good rule of thumb is the bigger a star is, the shorter its lifespan, the faster that star burns out. And so the first stars were incredibly massive and incredibly short-lived. But they were still pretty important, because fusion in the core of those stars created, out of hydrogen, elements, you know, like oxygen, nitrogen, carbon, all the way through iron, were formed in the cores of the stars. And then when those stars died and went supernova, in that violent explosion, all the other naturally occurring elements, basically through uranium, were synthesized. And so those first stars basically took the universe from a cloud of hydrogen gas in space to a cloud of hydrogen gas with a little bit of spice. And that spice is pretty important, because that's what we're made of. Quasars were also very common in the early universe, and I mention them because some imaging of them has been done here at the JJMO, or some work on that. You run into Mark Polanski outside. He was working on that, along with some students, I believe. I don't know how far they got with it, but we were working on imaging these things. Quasars, there's an artist's interpretation of a quasar over there. They are massive black holes, and they are, counterintuitively, also one of the brightest objects in the universe. If you ever seen one of those, those things that sometimes they're in movie theaters where you roll the penny down and it, you know, it's sort of a funnel shape. Yeah, okay. And the penny moves faster and faster the closer it gets to the hole in the bottom. Basically, quasars work the same way, or all black holes work the same way, really, except the penny is a bunch of charged particles, and it's moving a lot faster. So basically the incredible gravity of the quasars accelerated particles to close to the speed of light, and they were jetted out, I guess the poles of the black hole, in those jets you can see, which are called relativistic jets. And if one of those happens to be pointed at your telescope, then that's one of the brightest things in the entire universe. Quasars can be as bright as an entire galaxy. Sometimes supernovas are brighter, though. And so we've done work on imaging those here at the JJMO. Quasars are something we can only observe in the early universe, though. So it's pretty tough to image them. Even though they're so bright, we have to look very far away to see them. We have to look really far back in time. And that's because, and you might have heard, Stephen Hawking is famous for discovering this, black holes are kind of leaky. When the quasars had consumed all the fuel around them, eventually they evaporated. After billions of years, the black holes ran out of fuel and evaporated. And so today we don't have any quasars, because we still have black holes, but none of them are that massive, because there just isn't that kind of mass floating around in space. Which is too bad, because quasars are kind of cool. So the first generation stars didn't last very long, and when they went supernova, their remains were incorporated into a second generation of stars. And so stars today are of a third generation, made out of the remains of that second generation. We can actually, when we observe stars, we can actually distinguish between the different generations, which is pretty cool, because we can do so by figuring out how much metal is in those stars. So third generation stars, which are like our sun and, you know, Alpha Centauri, the stars you can probably look at in the telescopes outside, they have a lot of metal in them, because heavier elements, like metals, are made in the cores of stars. And so their third generation stars have had 2 generations before them fusing those heavier elements. Second generation stars, which we have observed plenty of them, they're just a little farther away, they have relatively low metal contents, because there was only 1 generation of stars before them to make metal. One thing we're still working on in astronomy is that we have yet to observe a first generation star. So, yeah, that's something we gotta work on. Calculations, or equations, predict that the first stars would have appeared around 560 million years after the Big Bang, but we have yet to observe one, because they're so far away. But we know we would be able to figure out whether we'd seen one, because they would have little to no metal in them, because there were no stars before them. And so, not much happened, you know, for the rest of the universe. I mean, you know, galaxies were born and merged, and stars were born and died, and once enough heavy elements had been synthesized in fusion reactions so that you could get, you know, like rocks and dust and stuff, solar systems began to form. And about 4.5 billion years ago, a pretty average yellow star formed in the middle of a cloud of gas and dust, and some planets accreted around them, and one of those planets has life on it, and thinks it's pretty special. So that's the history of the universe, and now we can look forward to the future. So there's plenty of astronomy that needs to be done in order to further our understanding of the formation of the universe. So if anyone's interested in going into astronomy, don't worry, there's still jobs, probably. Obviously we're trying to observe first-generation stars, but there's still plenty of observation that can be done so we can learn more about how the first stars formed and how the first galaxies formed. And right now, the Hubble telescope, which is the one on the right, is up in space, imaging, or sometimes imaging, things from the early universe. But the Hubble telescope isn't really specialized for that. If you remember when we were talking about the CMB radiation, cosmic microwave background radiation, we were talking about how that light has gotten stretched out as it's traveled towards us. Well, the same thing is true of light from the first stars and galaxies. As that light has traveled towards us, what was once visible light has now been stretched into more in the infrared range. And the Hubble telescope isn't really specialized for infrared observation. And so that's why we're sending up this telescope on the left, on your left, my right, called the James Webb Telescope, and that one's specialized for infrared observation. So that means this telescope will help us look even farther back into the history of the universe and see all kinds of cool new stuff. Hopefully allow us to shed some light on the formation of early stars and galaxies. There's also a lot of pressing questions in theoretical physics. First of all, uniting the Pepper family, uniting gravity with the other 3 forces, which is pretty important because that would allow us to describe the Planck epoch. And, you know, that's kind of an issue. Right now, the equations of physics, which are supposed to make predictions, accurate predictions about the entire universe, don't work for part of it. And that's kind of an issue. There's also problems with inflation, you know, how that happened, why it started, why it stopped, or whether it stopped at all. And that's one of the places where the multiverse theory comes from. If anyone wants to come talk to me after this about that, it's really cool. But I guess the big question is probably, what exactly was the Big Bang? I mean, what was that? You know, somehow, out of nothingness, a universe appeared with space, time, and matter and energy. And right now, physics doesn't have an explanation for that. And so that's one of the most pressing questions in theoretical physics. Because once we can understand the Big Bang, we believe that we'll be able to understand the entire universe. If we understand the mechanism for the Big Bang, we'll probably be able to understand, you know, like what's inside black holes and how inflation works, we hope. But we haven't gotten there yet. So there's a lot to be done, and there's a promising future for astronomy and physics. So thank you for coming out tonight. If you'd like to visit us online, those are our social media handles over there. We've got a website, we have a Facebook, we have a YouTube. You see over there, this is actually being filmed. So all this, a lot of the second Saturdays are up on our YouTube channel, and they're also live streamed. So if you're not around and you want to watch one, or you'd like to go back and look at an older topic that you're interested in, you can go see our YouTube channel. We also have an email if you want to have, you know, comments, suggestions, you just want to say hi. That's cool. If you're really into astronomy, you could become a volunteer, and you should be into it because astronomy is so cool. So join us next month for another installment of Second Saturday Stars. Thank you. I guess I should ask, does anyone have any questions? Yes.
You say that the Big Bang is going out and we're looking in. So how did they learn that they were looking in the direction of the Big Bang? I mean, was it because the speed is coming at you? And if you look left and right, the speed is different? I mean, how did they know they're looking to where it originated?
Well, we don't know where it originated. You can look all around, basically.
Okay.
Because you're not looking at, like, the place where that happened. You're looking more at, like, the time where that happened. So if you look really far out in any direction, you're seeing what that place looked like really far back in time.
Right, okay.
So in theory, if we could see through the opaqueness of the early universe, if we looked far enough out in any direction, we could theoretically see the Big Bang. But we can't because the universe was opaque. Just too bad.
Thank you.
Anyone else have a question? Alright, cool. Thank you.